Where did it go? So today, what I wanted to cover is essentially just cover the bits of the memory allocation interface and how it actually integrates with the with Rust, and then talk about how we can construct the page table. So essentially, the idea is that last time we discussed allocator in like a fair amount of detail, so we kind of understand how it should work. And I'm almost ready to assign the homework, so I will type it. I typed half of it, but I will type, like, fill in the details, hopefully tomorrow morning, maybe tonight. And then we're ready to essentially use the allocator, allocate address spaces, and create the very first user process after that. But anyway, so the idea is that this lecture is based on Philip's blog post, because he has decent text on how to integrate the allocator with Rust, right? So at a high level, the idea is that sorry, hopefully it should fly. Let me click this one. It's working. Yeah, cool. So at a high level, he has just like a generic write-up about what needs to be done for the memory allocator to work with Rust. But the main idea which you have to remember, so first remember that Rust has this linear ownership model, right? So it tracks ownership of objects, right? And it uses this box primitive for allocation. So essentially, this is a standard way of allocating stuff from the Rust programming language. And typically this box primitive, what it does, that internally it calls an allocate function, this one, which your runtime implements. And typically when you're running at user level, like whatever part of the Rust standard library or core library implements this method. And in our case, since we want to use box in the kernel, it's not that we're going to use it a lot, but just to have a. In fact, I mean, like the very last kernel we built does not use box at all and does all memory allocation manually, in a way similar to C. And in a way, in this kernel which we're building, a lot of stuff will be allocated manually. So, for example, when we allocate a page for the page table, we still allocate it manually explicitly. Why is that? So technically speaking, you can use box. But I don't know, just like probably just to avoid running into the fact that box implements a drop method as well, and running into this problem that, you know, when you like, if accidentally your allocated page goes out of scope somehow, the drop gets called. But honestly, I don't have a good argument. So maybe someone who knows Rust very well, like Talia, maybe she would be able to comment on that. I'd say makes no sense, but majority, like page tables will be allocating manually, like by calling a function, but maybe it's something like inter-process communication endpoints we will be allocating from box, right? And so essentially the question which we want to solve is that how we hook up this language level primitive box with our allocator, which we are building, or as a homework, right? And the ones which we discussed yesterday or on Monday. Okay, cool. So the luckily Rust has a decent interface for how to do this. So what you do, you place something like saying that you're going to be using this alloc crate somewhere in your in your kernel. Then you say, look, please consider like Philip writes what it really means, but like essentially the compiler says, okay, I expect to find the allocator crate. And after that, what you need to do is that you really need to implement this global alloc trait for your code. And what this global alloc trait looks like, it looks something like it implements these 4 methods. So it implements alloc and dealloc, alloc zeroed, meaning that the memory which will be zeroed on the allocation, and realloc, I think, moves the stuff in memory. So really, we only need maybe alloc and dealloc to get going, because everything else, I don't think we will be using any of the other methods, but we can think about it. And this layout argument essentially specifies like alignment and size of the object which you are allocating. But like if you're using box, all of it will be passed from the box method. And if you're using like really, I don't think you will ever call those methods natively, because for allocating a page for the page table, you can just probably implement a different interface. But essentially, and the Philip goes on and on for how he he says, okay, I'm gonna be building this allocator. I will implement those methods for dummy, stuff like that. So in the end, what's important here, you need to let Rust know which instance of the allocator to use, and you use this global allocator attribute. And you effectively will say, okay, this is the instance of my allocator, so please hook up with this one. And it's all good, like Philip goes on and on. Actually, he builds a reasonable allocator, but what I wanted to probably highlight is one more meaningful implementation of the allocator from this Redleaf operating system, which we built a couple of maybe 4 years ago. And effectively, Redleaf was also like a flavor of a microkernel, but and the source is open, so you can always click and take a look. And in my lecture, I will be using Redleaf as a reference, roughly speaking. It's not that I'm extremely proud of the implementation. Various reasons. It was our first Rust project. Like a lot of people, including myself. It's not that I'm better now, but those other people are better. But okay, if you get lost and you say, look, I completely don't understand how to go forward with the homework, you can always follow those links and take a look at how we hook up the alligators in Redleaf. And so here we do exactly this. So we say, look, please use this. We create an allocator, a safe zone allocator. And in fact, Redleaf uses body internally. And this version of body actually was implemented by Gerd, like I mentioned him, Gerd Zellberger, who was a collaborator on this project. But we just took his stuff, like his code base, and put it in Redleaf. So essentially, again, if you completely, this uses a slightly older version of Rust, but if you completely, if you're lost completely, so use Redleaf as a reference implementation. And what we do here is, if I want to, for example, essentially here is the implementation of this global alloc trait in Redleaf for safe zone allocator. So alloc, we implement alloc and dealloc here. So alloc, dealloc, actually, I don't know why we don't even implement the other methods. That's surprisingly it runs. But essentially, roughly speaking, it kind of like in our case, we have a full body underneath us, right? So it's not a big deal. Not surprising, but in your case, your allocator will be only able to allocate objects of two sizes, 4 kilobytes and 2 megabytes, as we discussed last time. And there is a couple of things here. So we place it, so since we use this allocator is immutable, right? But which means that just to avoid a mutable global. And so here we put it under a mutex we say that the lifetime of this object is static, but we put it under mutex. And you can do something similar in your code as well. And essentially just this is our new method. We just say, okay, look, we allocate this a version, an instance of the allocator under a mutex, right? And then this alloc and dealloc traits are essentially we take the layout, and that's the reference code, which you can also use as inspiration, I guess, for your own code. So you can follow, but essentially in the end we end up calling body. Let me just so here, if specifically, if we're allocating an object of a page size, we get a frame. So essentially from body, how do we do this? frame body allocate. So essentially, there is a method in the body which allocates as a frame. Not this one. But essentially, you can read through the code and nothing will be super surprising about it. Just where did I? Sorry, I just got lost here for, where was I? It's here. And that's essentially what you have to do in the homework as well. Okay, hold on. So is this makes sense, right? So the point I bring up the code is that everything what we discussed last time, you kind of like using this, and I will use this code in the homework as a reference, like pointing you to those source lines, explaining what needs to be done and stuff like that. That essentially, that's, oh Jesus, that's wrong. It's actually completely wrong. That's a part of the core library, not the kernel. This is us here. We get back to my source code. So essentially, that's the idea for how to build it and hook it up. Any questions about it? No. Okay. Yeah. No, it's not very interesting. So what we need to do here is, however, so this is the plumbing for the allocator. So another missing part, which was there as well, was this boot info data structure, which we like essentially from where we get the amount of available physical memory. So again, I said that we're going to be using Philip's description of boot info. I'm not exactly sure that he talks about the same boot info. So let's just quickly go back to Redleaf to just understand what's going on here. So at a high level, what happens is that when we start on top of a grub bootloader, grub talks to BIOS, or grub can start on top of UEFI as well, and figures out like uses low-level interfaces of BIOS and UEFI to figure out the layout of physical memory in the system. And then essentially when we start, like essentially when we go somewhere like, just quickly figure out the location for you. When like essentially we go to the very first part of the bootloader, and in homework 1, you build a very similar bootloader, but I deleted those lines for you. So essentially, when we just get control from grub in the start label, we can call into this check multi-boot method. And check multi-boot, essentially what it does here, it performs a check that EAX register contains this magic number, meaning that we are actually booting on top of grub. And this number matches to something what is called multi-boot specification version 2. Version 2 is a little bit more complicated than version 1. That's why I'm not sure whether, okay, the way Philip talks about it, he built himself a bootloader crate. And I assume that if it's like sophisticated enough, the bootloader crate handles all this transparently internally, right? Okay, that's one way to go. And in general, that's okay, but I wanted you to be exposed to those low-level details. That's why I said, okay, like, instead of using his bootloader crate, let's just really do it by hand. So the idea here is that if we're putting on top of this multi-boot specification, the specification itself is actually hard to parse because it's a very dry piece of HTML which sits somewhere. If you ask ChatGPT, it kind of lifts reasonably well what's going on in this specification. But the idea is that the rule number 1 is that EAX has a magic number, and that's what the code is doing. It says, okay, we're really on this version 2 of multi-boot specification. And if yes, then EBX contains a pointer in memory to a data structure which is defined by this specification. And what we're doing here, we're saving it into this bootinfo variable. So essentially, like before we polluted any registers, right? The moment we started on top of Grub, you will have to extend your bootloader to make sure that you read those registers, do this check for magic, and then pick it up from EBX. Anyone booted on top of UEFI? No one there? Good. That would complicate. Then I would probably have to redirect you to a crate which picks it up from the UEFI. Okay, this bootinfo variable in assembly, we just say, look, it's a global defined elsewhere. So if we see how it's defined in our code base, let me quickly search for it. So we actually create a static variable for it in Rust, this one. And that's essentially the way to make sure that this variable is visible inside the assembly. So we say extern C, no Mango. So the compiler will preserve this name, right? And it's simply like a row pointer. What we do next with it, we say, look, okay, we want to pass it to our nice, safe Rust code. So if I search for it again, somewhere in the main function, before we initialize the memory allocator, we essentially say, look, what we do here, we implement our own small multi-boot version 2 crate, and essentially we say load it from this address. And this multi-boot crate essentially handles, like if we do something like this, it handles the layout of this data structure. Let me switch here again. So dry HTML specification, and it's worth kind of cross-checking what ChatGPT tells you, but at a high level, it supports objects of different types, and like it has like a notion of a tag which has a type and has a size. And the type you're interested in is this memory map. So it's type number 6. In our multi-boot crate, let me show you. When we essentially trying to load the memory tag, we use the type 6 here, right? So and again, I will give you this source code so you can use it, and hopefully it still runs and works, but if anything, you can debug it a little bit. But the idea is that, okay, that will parse this data structure passed to us by Grub in this multi-boot specification. Again, roughly speaking, what it will look like is like kind of like this. So tag header type 6, it's whatever memory map. And then it goes with a bunch of entries, like with an address and LAN. And the trick here is that really on real server machines, memories might have gaps. So not all memory is usable. Most likely when you, and those types are defined here. So you essentially, there is a usable RAM, there's something reserved, there are some ACPI memory map to IO or stuff like that, right? So essentially just, you can take a look at what the code does, but essentially when we pass this data structure to the memory manager, like essentially here, what we do is that we initialize the allocator, and you kind of have to do something similar in your code, just because you're initializing, remember, we're initializing this 2 linked list, like 2 megabyte page linked list and a 4 kilobyte page linked list. So essentially, you will have to pass this metadata. What we do here, we just essentially implemented this init body method, and you can also take a look at it. But we essentially like iterate over all the memory areas in this tag, just pick up the sizes, and we shovel them into body. But you will be just working with your memory lists, right? So what is there?
Your comments are funny.
It's not even probably mine.
Or they said the first.
Yeah, there were some issues because which should not be issues for you because you most likely will be only booting on top of QEMU, and I think that one will not have gaps. There will be some reserved regions, I believe, but essentially you'll be fine. Here, maybe we're simplifying and like we might not initialize even the whole memory, so which is not a good idea. But okay, at a high level, this is the story. I just wanted to go through it because unless you kind of like have some high level understanding of what to expect, you might get lost, right? So we got the boot info. So, but it's passed to us, and this multi-boot crate, which I will give to you. I mean, hopefully it works. Will help you. That's clear. One other thing which I wanted to quickly discuss is the following. Oh, Jesus, I'm not sharing screen. Not fun, but it's okay. Forgot to share. What I wanted to say. Okay. So, okay, at this point you will have, so like essentially your logic is the logic is to implement the plumbing, making sure that the box is wired to the memory allocator, and inside main, essentially inside main, we handle like in the bootloader, boot ASM, you have to add handling for boot info. And here you will also kind of like handle boot info and handle init of your allocator, right? Because like, hold on, we understand that, okay, allocator only after this point, after you init the allocator, you can use it, right? And only after here, your box will return something meaningful. Because this initialization of the allocator, which takes boot info as an argument, essentially will read the memory map of the machine, and you start from this end symbol, internally allocate this metadata region, which we discussed page array, or I forget exactly what we call it, page array probably. And after that, this memory will go modulo some gaps from the boot info region, goes on your allocator list, right? That makes sense? That's how we kind of agreed it. And after that, you can do box new, and it will fly, right? Up until there, everything has to be statically allocated in the data section of the kernel. Make sense? And we're still running just one CPU, right? And now we're ready at this point, the subject of our lecture is, at this point, what we want to do is we want to create a kernel page table, right? So again, we can go about it differently, right? I guess one of the simplest way to go about it is similar to x86. So essentially, we will have one kernel page table, and we will use this kernel page table the moment we create it and initialize it, like load it in CR3, and until we switch to the first process, right? And then we will be switching between processes, and each process will have its own address space. Like I was talking about it, right? So if you have a proc data structure, it will have its own page table, right? And so normally we probably will never come back to this kernel address space, but we might if the very last process dies or terminates, right? And so at this point we will get back to the kernel, or maybe depending on how we decide to build the scheduler, we might be staying on this kernel address space if we say that, okay, an idle loop will be just spinning on this kernel address space, right? Makes sense? So the very first thing is to create this one. And again, so since there is no user part of the address space, we're going to be just mapping one-to-one, like I'll draw virtual address space on top. And we'll be mapping memory one-to-one. This is virtual. And typically people call it identity mapping, right? So essentially this page maps directly to this physical page, right? And right now, like when we put it, we have some funky page table from the homework, which maps some, I forgot exactly, 4 megabyte or 8 megabyte of data space, something along those lines. But we will map from 0 to the max address, which we get from the put info map. Make sense? Okay, and for that, we need to implement a couple of helping functions, right? So at a high level, creating an address space is not a big deal, right? So what you do is you essentially say, look, actually, let me ask you, so what do you think, what is a nice, convenient interface for this abstraction of a page table which maps virtual to physical? Wait, do we even remember how the page table looks? Yeah, do we need a refresher on this or not? Intel 4 levels, all good? No, like 5 on a very modern hardware, but forget about 5th level. Let's just stick with 4, easier. So what's the interface? What is a convenient interface? The expectation is, like, and here again, we can take inspiration from x86, right? Do you remember how it was done in x86? What was the method? Or what were the methods which were providing those? In fact, we're doing something very similar to x86, like we're building this kernel page table, mapping, roughly speaking, the kernel part of the space, right? Exactly like x86 was doing. We could even like build some method like map kernel, and which takes, I mean, if it's a part of the address space, it takes self. But if it's, yeah, that probably makes sense, right? And then every time we probably can have a different abstraction for map user, but essentially, what is supposed to happen in this map kernel? Do you remember how x86 was doing it? Anyone? No one remembers x86. So like x86 was doing the following. So it also was using an abstraction of a memory map. I forget exactly what the variable was called, but it was array with 4 entries. And at a high level, each entry contained the following information. So it was virtual address, physical address, size, and flags. And essentially, this map was defining where to start in the address space. So for example, at address 0, where to start at a physical address, because they were, x86 can start with a shift, and it can map with a shift. And in fact, physical address 0 was mapped at 2 gigabytes in x86, but in our case, we will map 1-to-1. Then we say a size of the region, and we say what flags, how we want to map this region. And typical flags would be something like read-only, writable, executable only, or something along those ways, right? And this will, if we build a function which takes those, roughly speaking, these 4 things, then we can say, look, now we can manage our address space like reasonably correctly. So we can map this region from 1 to first megabyte where we place the kernel with read-write permissions, then read-only part of the kernel we can map with read-only permissions. So it's a text and read-only data section. Then the rest of it, including the page array and up until if we are very careful, I suggest we skip the gaps to make sure that they are not mapped in the virtual address space. Why is that? Because if it's unmapped, then access to this unmapped region will give us a page fault. Inside the page fault, we can just say, okay, it's a bug, and immediately kind of fault it to the kernel or panic. If you leave it mapped and write into this inaccessible memory, which BIOS passed to us, consequences can be different, and it's not clear that the bug will be immediately triggered. Maybe it will be something like a machine something exception, but not clear. So I suggest we should skip the gaps in the boot info, but really just map everything as read-write. Right? Makes sense? So essentially, we can control it with the flags and which addresses we map from virtual to physical, right? Makes sense? So one tiny detour here. Remember, I keep saying that we're going to be using we'll be using those symbols like and stuff like that. Let me show you. Does anyone remember how to add those symbols to the kernel? How do we know where the kernel starts, where the kernel ends? Like essentially
the linker symbol N.
Yeah. So let me show you how it's done. Again, we can use Redleaf actually as a reference implementation. Kernel base, for example, is a good one, I think. Kernel base. Really? Just trying to find the piece of code which uses it for mapping. Here, maybe? Just a second, guys. Yeah, so this is reasonable. So let's search for something like kernel and let's see how we define it here. So at a high level, Talia, you're right. So we just essentially, what we're saying is that we're going to be using the linker script to make sure that this symbol is visible at the level of the code. Let me just make sure that we understand the details. And trying to hide this one. Actually, is there an easy way to this one? Okay, this one. And this one, but why March? Honestly, was expecting it to just quickly see how we use the linker script. I should admit I did not. If you see a linker script, let me know. But where is it? March. I think really. Just quick exploration of the build system. Oh, Jesus, region and Rust. Okay, linker. Handle. Oh. The thing when I left this kernel, I had a linker script, but someone did it over me. But which is fine. So they did probably a better job, but I wanted to. Like,
Is it linker
This- no, this one. Sorry, like just code reorganization here. So, I assume this is here, right? So, what we're doing here, and in a homework, when we like, if we quickly switch to the to is that just quickly say hello s or something. Where is it even? Does anyone remember? Part of Mars. Okay, I cannot find a repo apparently. So
It's your Mars group slash hello.os.
thank you. But why don't I? Search. Yeah, so in our build system, if we switch to the Rust branch or something like even like homework one, then I figured I remember I left a linker script, so it is there somewhere, right, in SRC. This one. So this is the linker script, and actually, I don't know, maybe, so right now we don't have any symbol here. So essentially we just say, look, please, when you link, this is how you position the sections. And like it's not a coincidence that we actually place the read-only data and the text sections together so we can map them read-only. So in my drawing, they're flipped, right? But essentially here we say, look, guys, we wanted them together. So this will be mapped read-only. And so in Redleaf, we essentially introduce a couple of symbols here. I think actually these are visible, like read-only data, but essentially this and symbol, which we put here at the end, will be visible at the level of the language, so you can use it, and then in a manner similar to how you let me show here. Pop-up text end. So essentially, this is our wrapping around those symbols, so we essentially expose them in a cleaner manner. So kernel end uses the symbol which I was just showing. So this is double underscore, and essentially we use then those functions which later in the code, which we essentially, when we start mapping memory, we use all these symbols in a way show you here. I'll take what's back. Probably expose them somehow differently as well, because we just seen the kernel end as well, and Kindle this one. What I'm trying to get to is the and symbol. But we're here. Oh, and.
I did a grep. I think it's kernel source memory mod name underscore underscore n. Oh, is it in the top search result?
No, somehow Arch exposes kernel end, but I don't exactly know why. Let's take a look. So the expectation here, so how do we use kernel end? Just a sec. I mean, and maybe those details are less important. What's important here is the like, I mean, probably this is the function which is worth looking at. So essentially, what we do here, and again, I kind of suggest to follow this this architecture, is that we say, look, we implement a map generic function, which essentially, roughly speaking, takes the same argument. So it says, takes the virtual address, physical address, size, and the flags, like for example here. And what we do is this map generic function, and here we say, look, from the kernel base to the kernel base, like essentially we use those text ends. So essentially this essentially we're mapping those parts of the kernel, like I was saying, one by one, maybe from like essentially from read data, okay, from read-only data start until the end of this read-only data end, we map as a read kernel. Essentially, read-only kernel for the text section, we map as read-write executable. For the and probably for the rest of the kernel, and here we use this kernel end slightly differently, not sure why. But essentially, at this point, the point is that we need to build this map generic function, which essentially internally can handle the mappings and like essentially implement the logic of the address space, right? And this is what essentially I wanted to discuss. Really, is like everything else is more or less as a background, is a background, but what we really need to understand is how to build this a function which takes these four arguments and essentially maps them into a specific region of physical memory. So let's quickly essentially outline, and this is kind of the main subject of our lecture today. So essentially build this function. So if we're building something like map generic, which is similar to what x86 had. So essentially, remember I said that x86 takes this array and it had this map function. Let me actually maybe bring it up real quick. But does anyone remember what was inside this map? How was it organized? And this is essentially, this is what we want to build here as well. It's not that I remember where it is, but can probably find it reasonably fast. Just real quick. So this is the kernel map data structure, which we're using to describe the regions. Quickly. Okay, maybe here. Start from this one, and then just search for K-map. Just a sec. Almost there. So essentially, K-map as a data structure, we describe this four regions. This is exactly the one which I was trying to explain here on the map. And where do we use it for K-map? This is their map generic function. So this map pages. So can someone like kind of like guess from the signature of this function
And the logic map pages essentially maps into a specific address space, which is pointed by the page table directory. It maps starting from virtual address kbird, specific size, to a specific physical address star with specific permissions. And that's the function which we want to build in our kernel as well. So what's inside this function? Essentially, the idea is map a page from here, in our case, 1-to-1 to here. In case of it, like we can probably implement the generate function as well, meaning that we can map with a shift.
So what's inside? Let's wake up for a second. This interactive teaching. Okay, but let's think about it. Okay, it took me a while, so I understand that you guys are falling asleep at this point. But let's think of what. That's the real, like, it's this function is core of homework 4. Essentially, we will use it to map to build the address space of a user. But it's a generic function, so we can also use it to map the kernel part of the address space, and then map each time the user will be allocating some memory, like we said, we can load some L file. We'll use this function to map some additional memory from here to the user. Like anyone, no memory of x86? Who was in the x86 class to begin with? How many people? Not too bad. So Josh, you wanna guess what's there? What needs to happen? So we want to map virtual address into a specific physical address. How is it done?
From what I remember from my iOS class from UCI, the virtual address, there's parts of it that lets you go to the page table, and then you go down, if it's multi-level, you just keep going down until you get the physical page.
Correct. Do we remember the parts?
I think one part of it was like a pointer, and another part was like the offset. So there's like a pointer to a page table, and then there's an offset in that page table. And then that entry will be another virtual address, which will be a pointer offset.
Hold on. I mean, this is the address. So the lowest 12 bits, if we're mapping a 4 kilobyte page, any address from 0 to 4095, right? 496 is addressable by those 12 bytes, right? And then we split this address into chunks, right? In our case, because the page table has 4 levels, do you remember what the size of those in the bits? What are the? How many? Wait, I've heard what the number?
It's also
Well, why 12? No memories? What's the logic behind it? I mean, I never remember myself, and it changes from architecture to architecture.
so also 4096.
Imagine if this is the root of the page table pointed by CR3. And like this is PML4. Our goal is to figure out the location of the next level in physical memory. So this will be physical address. How many entries are in the root? You're right when you say that will be the whole thing is 4096 bytes, but how many entries? What's the size of the entry?
4 bits.
On 32 bits, it's 4 bytes. But since we need to save the physical address, and in 64-bit address space, physical address cannot be like unless you make additional assumptions, is larger than 4 bytes, right? So then what's the size?
So it's the answer to the original question, like 9.
The answer is 9, but let's you're right, but give me the logic, how to arrive at this logic.
Because you just have 8 bytes and 64 bits. And that's 2 to the 3. So
Correct.
you need 3 less bits.
Okay, so the thing to remember is to kind of think about it in the reverse order. You say, what is there in a page table? There will be an entry. This entry will contain physical address plus some flags. Since addresses are large, they are 64 bits, then the entry, let's guess the size to be 8 bytes. But you say, look, but how can we fit flags plus physical address into the same 8 bytes? So what's the answer here? Do you remember? No? Anyone? Well, no. It's kind of important. So no one remembers?
The page table is 4 kilobyte aligned.
Correct. So the next level will always be 4 kilobyte aligned. And that's the design contract with the CPU. They say if you don't align them, then nothing will work. And since it's 4 kilobyte aligned, the 12 bits, those imagine this is an address to this, it's a different address. It's this, but physical address, right? But the lowest part of this address, those lowest 12 bits will be all zeros, right? Just because it's aligned. So instead of saving those zeros here, they use this space for flags, and they just extend with zeros when they use it, right? That's why it fits into 8 bytes. And if it fits into 8 bytes and the whole thing is 496 divided by 8 bytes, you will get that we have 512 entries in one level, right? That's why this will have 9 bits, right? So I don't remember what Intel says about those upper bits of the pointer. Most likely it says that this should be 0 unless you use some additional hardware extension, which says, okay, it's some kind of a additional hardware feature. If they are not 0, I think it should crash. But essentially those 9 bits of the, essentially it will have for each level, since we are on a 4-level page table, those 9 bits will be an index into the root or PML. I forget what PML stands for. Page memory level 4, I guess. So, and those bits will define the entry here, right? Agree? And then obviously, I was asking if you remember how the page tables work, and if you need a refresher, but this is the refresher essentially. Okay, the goal is to finish, so let's just quickly do it. So here, the physical address points to the next level. Let's call it PML3. Well, it has a different name, but it's easier to talk in terms of PML3. Again, the next 9 bits will choose an entry in this level. Again, there will be some physical address plus the flags. This will point to the next level here, right? This 9 will choose an entry here. Again, physical address points to the next level. So if this is PML 2, oh, sorry, this is 2. This is PML 1, right? And finally, this 9 bits will pick an entry here. Again, physical address will point to actually location of a page in memory, and those 12 last bits will choose a byte address within the page, right? Makes sense? So every time when we map a virtual address into a physical address like this, right? We need to do what? I mean, this is the valid mapping, anatomy of a valid mapping. So it has to be created. So more specifically, what steps are we going through here?
I guess this is translation. That's the word for it. Or are you asking the next step?
Mechanically, how to write a code for this map generic function, which takes virtual address, physical address. Let's imagine we're just mapping one page, so no size, and takes flags.
the end goal is to create this, obviously. This is the, like you say, translation ability mapping.
Well, I know the register points to the first table. There's a register. So you use that and you split up the virtual address into pieces.
Yeah.
You use each and you just jump through them until you get to the end.
Correct, almost correct. One important thing. So you mentioned that the CR3 register points to the address space. Might not be the case because typically it's not always true that you're mapping into the currently used address space. So in some cases, like imagine it has it's a member function, whatever function of a class. So you will have something like self as well, and this self will contain the pointer to the root, right? Okay, cool. So then we assume that self and the first level is allocated when we created the new instance of this class, right? So this first level is allocated, right? So as you say, we take a virtual address, we take the top 9 bits, we try to go and look up this entry. There are two possible cases. It's either it exists, or maybe we never mapped the next level before, right? So we have to check. If it doesn't exist, we need to allocate the next level from the memory allocator, like your alloc page interface, which allocates a 4 kilobyte page, right? Agree?
Would this be a page fault?
No. Okay, good question. I mean,
Well,
actually,
because you don't access it.
yeah, you don't access it, so
Yeah,
it's
okay.
all like logical in your brain. And in fact, CR3 might actually have this valid mapping, but you don't touch it, right? But good question. So why, when we even read this location in memory, which contains this, and it's typically called page. Okay, I would say it should be called PML4 entry. But depending on which crate, and I will show you the crate which we're going to be using, it will be called like a different name, slightly different name, but same semantics. Why, when we even read this location, why don't we page fault? Just an easy question, but who can explain? Like, it's also important to always keep those in mind. This is our physical. This is our virtual. Why don't we fold? Like there is self. Self has a pointer to PML4. It's a virtual address, right? Because if we want to resolve itself to PML4, it should be a virtual address, right? Everything what we can access is the virtual address. So why don't we fold? It's a simple argument. So just.
Is it aligned to a crazy high amount, so you don't need all of the lower tables to resolve that address?
Okay, maybe I sometimes have issues with how I ask the question, so maybe you don't understand the question. Excellent.
Maybe there's a flag set in there that's like, oh, it's not
Hold
allocated.
on. I like, this is my kernel sitting here, right? This is my metadata page array. When I created an instance of this class, I don't know what to call it, this space. I said something like new. Internally, I called page alloc to give me PML4 address, right? Right? This is the virtual address, by the way. So what does page alloc return me? That's why this is this page, right? So I got it from the allocator when I created an instance of this class. Where is it here on this map? Pick allocation. So that's my question. Essentially, I just want you to figure out where it is on the virtual address space.
After the page array?
Yeah, somewhere after the page array. I agree with you. In physical memory, and since we map one-to-one in virtual memory. And here is the tricky question. Did we map or not? What is currently mapping? What is currently mapped?
inside the main function. I just cut you on the debugging time, otherwise it will take forever. But it's also nice. I mean, I don't know, but yeah, okay. What is currently mapped? What is sitting in CR3? It's not pointing here. It is pointing to some other page table. Kernel page table. Which one?
The one from boot.asm.
Yeah, the one from boot.asm.
So that one maps everything one-to-one, and we already have virtual addresses. So we can just use the physical addresses as the virtual.
Correct, but one logical flow you said maps everything. What does it map?
I think it maps the first 32 gigabytes of virtual memory to physical memory.
Correct. And it may happen that 32 megabytes doesn't even go beyond the page array, which
That
means
is
that
gigabytes, so it definitely does.
8 gigabytes?
Yeah.
Really? Wow, that was a good homework.
I
Then
thought it
where's
was- I thought it was 4 gigs. I don't remember.
I know.
even 4 gigs? I mean, it's unlikely, right? But there should be a runtime check. But you would like just again make sure. Okay, if we map 4 gig, then fine, we can access memory up to here, right? But be careful that you don't go beyond. Right? The moment you say, look, I will be allocating memory, and suddenly maybe the page array is initialized in such a manner that the very first page on this linked list is the very last page of the physical address space, right? Depending on the direction of how you choose to initialize it, it might be this one. Then you return this page here, and the moment you try to look into this page, you page fault. So, which similar to x86 kind of calls for kind of like two-stage initialization scheme. So maybe init allocator up to 4 GBs, up to the number which is mapped by the page table, and would ASM, and then build a new page table, hoping that there will be enough pages to construct this page table. And after that, the second stage, add the rest of this memory to the allocator, right? Then it will fly. So x86 does exactly the same, right? So this is like a two-stage thinking. But you got the point. So we don't fold here. We don't fold here because the virtual address which we got from page alloc is either like one of those pages. And since we're using physical and virtual addresses interchangeably, right? Because we mapped everything one-to-one, we don't have to translate between them, right? And at this point, this is a virtual address, so everything is nice, right? Got it? Okay, we didn't fold. That's good. We understand why we didn't fold. 2 cases, it's either allocated or not. If it's not allocated, you again go to the page alloc. It gives you either virtual or physical address, depending on how you want to structure this. And what you're doing, you're connecting the two essentially. You're writing the physical address of this page into this entry in the page in PML4, and you're writing those flags. Flags roughly match the flags which you pass, but you can deviate from it, and you can say, I will choose a different subset of flags, but meaning that you can, probably, like if you're mapping as executable, just put it here, honestly. I don't think you can avoid it, right? Make sense? And so on. So essentially, this is the logic of your function. So essentially, they say like it's either allocated or not. If it's already allocated, then fine, we don't have to do anything. If it wasn't allocated, go allocate this level. Use the next 9 bits as an index into the PML3 level. Again, the same kind of logic. By the way, I say it's either allocated or not. How do we decide if it's allocated or not?
Like I said, a flag might be sitting there.
Yeah, which flag, do you remember?
Oh.
Okay, actually bit number 1 is the present bit. If it's 1, then it means that it's present. If it's 0, no matter what else is here, then it's not present, right? Just wanted to make sure that we remember. But we go down this level, allocate, or maybe if the next level exists, you just don't do anything. You just go through. You just check whether the flags match, because if you're saying that I'm trying to, okay, that leads us to a different idea that probably you have to, not probably, but for sure, and I forgot about it, you need to pick the most permissive flags at the topmost level, right? Because if you're mapping this as read-only, then the entire range of memory, if you put read-only here, all of these entries have to be read-only, but it might be that one of them is read-write because the mapping is 4K, but this range is like terabytes in size, right? So you have to pick the most permissive flags and stop it only at the level which corresponds to the size of the chunk you're mapping. But if we're talking in terms of pages, just at the very last level, we'll put the real flags here. Make sense? That's an important bit, yeah.
If you did mark the top level table as read-only and the table itself was in the
If you
memory it addresses, then you could never change it back.
You can, but obviously the hardware, if you don't change, if you forget to change, you can change back. But if you forget to change to a more permissive set of flags, then when I say more permissive, I don't remember how Intel sorts those, so I have to look it up. I don't really. So I would say probably, I actually don't remember. I don't know. Like there should be some kind of a lattice, right, of permissions. And I don't know what this lattice is. But you can change, but if you forget to change, then the translation might trigger a page fault later on, right? And then at the very end, at the last entry for this one, this page, you say, you already allocated it and you already know the physical address. So this will be filled in from here, right? And at this point, you have the mapping installed, right? So your goal will be to write this function and essentially write enough abstractions on top of this function to kind of map not just one page, but regions of memory. But everything else is kind of like simple again. So I just wanted to quickly help you, just like literally, like we have 5 minutes. I suggest we use this crate, which is x86 crate. There are multiple crates which try to achieve the same. One is from Philip, right? And this one is from Gerd. I like the Gerd's better. Why? I don't have a strong feeling why. So just because I had access to Gerd probably and could ask him about everything. But essentially, this crate provides definitions for all the page table entries. So for example, if you go here, and also Gerd is I mean, I'm not saying that Philip is worse, but Gerd, like he writes very clean Rust. I'm pretty sure they both write very clean Rust, way beyond what I can write. But essentially you can take a look at, like, you implement PML4, this is like a neat tricks with bit flags here. So essentially, although this is for PML5, so forget about PML5. So just PML4, he encodes like all the bits. So this is the present bit, read write, stuff like that, right? So this is cute. So use this crate in your source code, making sure that you use those definitions. You don't have to write them from scratch. I suggest in a homework an abstraction of this virtual address space similar to a red leaf. Although, I mean, like you can push back and say, look, I don't want to build it. It's fine. It's your thing. But essentially here, when we create a vSpace, for whatever reason, here we use a box to allocate the force level of a page table. If I roll this code, I kind of argue that it's kind of an ugly way to do it. So I don't like box here. So I would rather put just an unsafe pointer here and use the page count explicitly to highlight the fact that the page comes from some magical allocator. It's not like a real Rust object. It can have a very funky lifetime, especially if the page is mapped multiple times. So by multiple address spaces. So I want to highlight this fact. So I would say don't do box or anything like that here. Although technically it works, right? And in this vSpace, I forgot. It has a nice collection of methods to implement, but for example, map identity mapping, but shift with an offset. Internally, it uses this map generic function. Map generic is the one which we just looked at. If you look at the source code, it roughly does what I just put on the board, checking if it's present, if the bit present is there. If not, allocating a new page table. This is instead of a name PML3, they use page directory page table or something like this, which is confusing because no one remembers the names of those levels. But essentially, what it gets here, it does this PML entry new. It does allocate one page here, so not a box, right? And it passes this page into this PML4 from Gert's crate, right? Let me go back for a sec if it allows me to go back. Probably doesn't. Map generic. Where's my map generic? Cannot type on this keyboard. I'm sorry, this one. This one will do. Just wanted to come back here to the source code. In the same logic, you descend the level by level, essentially. There is some tricks which we try to do with trying to fit into 1 GB chunk. Don't do anything like this. Keep the implementation as simple as possible. In fact, maybe map generic should map just simply one page in your case. And then you will build another function which maps a range or something like that. So, but anyways, my high level point is this. You can use this as some kind of reference implementation if you get stuck completely, but I'm not saying that this code is ideal. And I think I'm done. So this is what I wanted to cover today. Let me just quickly cross-check my slides, but this is probably what I want. Yeah, sure. So with this, we're done with page tables. So next time we will, I will abstract a little bit saying that, okay, you map the kernel part of the address space, user part of the address space, and then we'll talk about how to load something into this user part of the address space and get the first process running. We can get it running, but then we have to implement system calls to get back into the kernel, right? But we are kind of moving towards building the very first process. But anyway, thank you guys, and I'll see you next week. I'll see you for the office hours actually tomorrow if you guys are around and anyone needs